For each of the following molecules or ions, we will be writing Lewis structures, listing the number of lone pairs on the central atom, identifying the shape, and estimating the bond angles. We will be starting with phosphorus pentabromide. Phosphorus has 5 valence electrons. Bromine has 7, but we have 5 of them, so we must multiply the 7 times 5 and we get 35 electrons, for a grand total of 40 electrons. Phosphorus is going to be our central atom. Now we will surround the phosphorus with our 5 bromines. The next thing we will do is connect bonds from our outer atoms to our central atom. Each of these bonds represents 2 electrons. Our next step will be placing the other electrons that we have left. We set 5 bonds in the previous slide for a total of 10 electrons. So if we subtract 10 from our original 40, we have 30 left. Meaning we should be able to put 6 around each of our bromines, completing all of their octets and fulfilling all the requirements to make this a stable composition. There are no lone pairs on this central atom. Onto the shape of our atom. Our atom is going to look like this in a 3D rendering. So therefore, our shape is trigonal bipyramidal. And because we know that it is a trigonal bipyramidal, we can estimate the bond angles. We will have 2 90-degree angles represented by the red line and 3 120-degree angles between these bromine atoms. Our next molecule is xenon oxydifluoride. Xenon has 8 electrons. It is a noble gas. Oxygen has 6 electrons. Fluorine has 7, but we have to multiply times 2 here because we have 2 of them, and we get 14 for a grand total of 28 electrons. In this molecule, xenon is going to be our central atom because it's the least electronegative since it's a noble gas. Now we will place our 2 fluorine atoms as well as our oxygen around the xenon. Now we will do as we did in the first example. We will connect the bonds to our central atom. Now we will place the remaining of our electrons around the central atom and our auxiliary atoms. We must complete octets, so 6 must go around both of the fluorines as well as the oxygen, leaving us with 2 left over. And since there are 2 sets of lone pairs left over, they will go on our central atom. Because xenon is in a period lower than the third period, it has an extended valence shell, meaning it can have more than 8 electrons in its outer shell. And as we've already said, there are 2 sets of lone pairs on this central atom. Onto the shape of xenon oxydifluoride. It's relatively easy. As you can see, it's T-shaped. And the reason for this, instead of something more along the lines of trigonal planar, is because our 2 lone pairs at the top on the central atom are actually forcing our other 3 atoms closer together, because they want to be as far apart as they possibly can. The angles we should come up with are 1 180-degree angle and 2 90-degree angles, thus forming a T-shape. Our next molecule is the cation sulfur pentafluoride. Sulfur has 6 valence electrons. Fluoride has 7. But again, we have 5 of them, so we must multiply the 7 times 5 and get 35. But we cannot forget that we are also losing an electron because it's a cation. So we come to a grand total of 40 electrons. Sulfur is going to be our central atom in this molecule because it is the least electronegative, fluorine being the most electronegative atom on the periodic table. Now we must surround our sulfur atoms with our fluorine atoms, and we're going to arrange them like so. Again, we will then connect all of our bonds from our auxiliary atoms to our central atom. Remember, these are 2 electrons in every bond. Now that we've used 10 of our 40 electrons, we have 30 left, which luckily for us again is enough to complete the octet rule on the rest of our fluorines. Our molecule is going to look something like this, with no lone pairs on the central atom. The shape resembles that of the first molecule that we went over, in that it is a trigonal bipyramidal, meaning that we can also accurately estimate its bond angles. The bond angles are going to be the same as our phosphorus pentabromide was. We are going to have 2 90-degree angles as well as 3 120-degree angles. Our next molecule is iodine trifluoride. Iodine has 7 electrons, and as we know, fluorine has 7 as well. But we have 3 of them, so 7 times 3 is 21, for a total of 28 electrons for this molecule. Iodine is going to be our central atom for this molecule because it is less negative than the fluorine atom. Now we will place our fluorines around our iodine, like so, and then connect the bonds to the central atom and our auxiliary atoms. And remembering, each bond is like 2 electrons. And now we will place our electrons around our molecule. We're going to take our electrons first and place them around our fluorines to complete the octets. Any of the electrons that are left over can immediately be placed on the central atom iodine. Iodine is below the 3rd period, so it actually has an extended valence shell in the d orbital. So it can actually have more than just 8 electrons. There are 2 lone pairs on this central atom, which can help us figure out our shape. We can actually use the same 3D rendering to represent this molecule just like the other one, and it is too a T-shaped. And now let's take a look at our bond angles. We have another T-shaped molecule, so this will be relatively easy to estimate the angles. And our bond angles are one 180-degree angle and 2 90-degree angles. This is exactly like xenon oxydifluoride, which we did in part B. Our next and our last molecule is the anion bromine trioxide. Bromine has 7 electrons, while oxygen has 6. We have 3 oxygens, so we need to multiply those numbers and get 18. But we also have 1 free electron that we're adding in the mix because it is an anion, meaning that it gained an electron. So we should get a grand total of 26 electrons. In this molecule, bromine is going to be our central atom. And we are going to place our O's at a very different kind of arrangement, and I'll show you why in a second. But we're going to connect our bonds. And now we're going to place the rest of our electrons around our molecule. There is 1 lone pair on the central atom, which is causing a lot of this shape. Now getting into the shape, this shape is very different from all the other ones that we've seen in terms of the drastic effect that the lone pairs on the bromine are having on the oxygens. This shape is a trigonal pyramidal. The lone pairs are actually forcing the oxygens closer together, and I'll show you with the bond angles here in a second. But we can solve for these bond angles very simply by using the same chart that we've been using to solve for all the other angles. Our bond equals here are about 107, sometimes 109. It just depends on the strength of the central atom, but 107 in this case. And that concludes our video on how to solve problem 420.